I'd like to thank, first of all, the organizers for inviting me to give this talk, and also for David Bierling, who put me forward for it when he couldn't come himself. So today I'm going to talk about not work that I've done, but work that I would like to do. And I'm going to first talk about basically what might be involved in modeling cryptogamic covers and weathering. And first I'm going to give a quick introduction to what we know about how cryptogamic cover organisms weather minerals. And then I'm going to talk a little bit about how we conceptualize weathering today. And then finally, cryptogamic covers today and their implications for how one might model them in a process-based manner. So weathering depends on water, the minerals, and particularly their surface area, and then together with a weathering agent, for example, low pH. And there is a lot of literature out there indicating that lichens do enhance weathering compared to bare rock. And furthermore, that they may actually, in some cases, protect the substrate from abiotic weathering. For example, they protect from temperature fluctuations. But also that the morphology of the lichen is important. Stretch and Viles did find that there was a thicker weathering rind when it was a fruticose lichen as opposed to a crustose flat lichen. And furthermore, there have been several laboratory-based experiments recently that do indicate that bryophytes enhance weathering compared to bare rock as well. And I'm not going to dwell on this too much, but I think I will mention it simply because the idea has been out in the literature for some time. And when you're doing a process-based weathering model, you usually have a CO2 curve going into the soil. And so Keller and Wood suggested back in 1993, based on these field experiments, that you could have quite a lot of organic matter deeper in the soil with microbes, and you could actually have an elevated CO2, which would lead to higher weathering rates, and they suggested that this could have been the case in the Ordovician. In this case, we're looking at basically a deep soil with grass on it, and so that's the effect of the grass in the summertime, and this is in the wintertime. But yet way down here, this is a meter scale here, so 7 meters deep, we have quite a large effect on CO2. That's really all I'm going to say about that. I mean, we know that from experience, from experiments, that rootless plants are not going to just respire, they're not going to actually be a source of CO2 in the soil. But what about modeling? So the geocarb family of models, including models like the original version of COPS, plant weathering was controlled by an empirical function which did not distinguish between bare rock and cryptogamic covers. But the latest version of COPS has a new empirical function which distinguishes these two things, and it's specially designed for the Ordovician. And then there was the model that Tim Lenton told us about on Monday, which is the state of the art in biosphere modeling in the Ordovician. And this is basically a dynamic vegetation model written by Parada, which includes a simple demand-based rock weathering function so that they can estimate the weathering after they've estimated the NPP of the plants. And then there are my models, which I have attempted to take into account weathering by plants, but they're all designed for vascular plants, and they've never been applied to the Paleozoic. And so the obvious question is, well, why haven't I done it? And now I'm going to tell you a little bit about how weathering works today. And this is a map of CO2 consumption flux over the Earth. And you can see that there are several orders of magnitude difference between different places, and that the weathering is actually taking place in hotspots. As a matter of fact, 50% of the global CO2 consumption today is coming from approximately 9% of the terrestrial land area. So you do actually need a spatially resolved model in order to sort of tease that apart. And so where are the weathering fluxes coming from then? So denudation, which is basically both the physical removal of material via erosion plus the chemical removal of material within the regolith, which comprises the soil and the underlying bits and pieces, which I'm about to describe to you. So the soil is where we have the biological influence. We have plant roots, we have bioturbating organisms, and then underneath that we have this saprolite, which is usually defined as something that still looks a bit like bedrock, but you can get a hand auger through it. And then underneath that you might have like fractured bedrock with sort of weathering rinds on the fractures, and then underneath that you would have pristine bedrock. And so that's actually an explanation for what's happening in this so-called critical zone, where as we were told about in an earlier talk today, that there's a weathering front that is sort of moving downwards into this bedrock, and so you're ending up with a deepening weathering front, but yet there's also a tectonic forces raising the entire system. And then depending on the slope angle, you're also going to have mass wasting and the removal of material from the top of the system. And then of course the plant roots are constantly sort of developing new soil as well, and so you have constantly sort of moving weathering fronts there. And is especially important in sort of steep lands, because then you have removal of old weathered material and the exposure of newer, less weathered material, and making that available for attack by weathering agents. And this is one of Suzanne Anderson's diagrams. She's a person who's very much involved with understanding the critical zone. The critical zone is it's defined as being anything from the top of the canopy right down to the pristine bedrock, all the interrelationships and exchanges of material and energy in that whole system. And generally speaking, we're interested in how the water is going to move, because the water is going to sort of move the weathered materials out and provide fresh water for more weathering to occur. So Suzanne Anderson actually looked at such a steep catchment in great detail back in the 90s, she and her colleagues, and they actually elucidated exactly where the water was going with loads of lysimeters and piezometers. So this little catchment, it had been logged. It had conifers growing on, and then new conifers were planted. I think over a decade before they actually started doing these experiments, and so there's a colluvial soil which the average depth of that is less than a meter, and underlain by an almost equally thin sort of saprolite, and then finally a fractured rock layer under that, and then finally you have a fresh rock layer, and that fresh rock layer can be like up to 9 meters deep in this system. So the question is where the weathering flux is coming from, and they elucidated that half of those weathering fluxes are actually coming from that thin colluvial soil, even though it's basically punching above its weight. And that's of course where the plant roots are. And the rest of this, you don't need to read this in detail, but interestingly enough, of the other half that's coming from the lower soil layers, about a quarter of that is actually coming from the weathering front itself at the interface with the bedrock, because the bedrock actually has a very, very small proportion of carbonates, and there's no carbonates. They didn't find any carbonates in any of the weathered section of the sections, and they did have a drill hole that was like 30 meters deep, so they did investigate that, and several other drill holes as well, so they did investigate that in some detail. So now we're going to talk about a completely different system. So we're going to go to Iceland and look at this successional system. So we have a series of lava flows, and these are lavas, not pahoe ones with a sort of glassy rind. They're of andesitic composition, and they have soils on them which are almost entirely aeolian. The two earliest lava flows are exclusively populated by basically lower land plants and lichens, whereas the third lava flow has Impetrum nigrum growing on it, and then finally the oldest one has thickets of Betula pubescens on it. So the organisms in question here are Rhacometrium lanuginosum, which is a moss with up to 15 centimeter long stems in Iceland, and it forms these really sort of lush, pillow-shaped, dense sort of mounds. And then finally, we have also the Stereocolon vesuvianum, which is a fruticose lichen. So it has lots of branches. It's not just a sort of flat covering. It's quite a has quite a lot of branches. And these people looked at basically the depth of what could be called the soil. So this is measured from the top of the moss cushions. It is not measured into the bedrock or anything. In fact, these things are forming these soils totally on the lava. It isn't clear to me at all that there's much in the way of a weathering front going into the lava at all. So these organisms are epigeic. So how would I model that? Because my model has an exponentially distributed set of roots in the soil, and I obviously can't do that with this system at all. And in fact, nutrient uptake in my model is taking place in the root system, and in those bryophytes, it's actually taking place in the entire body if I've understood the online textbook of Janice Gleim properly. That is that the proton pumps are located all over the place. And if I'm wrong, please do correct me because I'm only just learning it. But and then the lichens and the mycorrhizal fungi. What if the system had fungi? So if that were going into like a sediments or a soil, then I don't know, maybe I could get away with some sort of exponential distribution going down into the soil, but I don't feel comfortable with that at all. It probably is going into the pores of the rock, or anyway. So then what about dryland systems? So there's quite a lot of cryptogamic covers there. And Williams et al. Have this paper with these fantastic figures in. And basically they have a conceptual model for dust capture. And if you think about it, the dust is probably like silicate rock in origin. And as a matter of fact, there was an old controversy about lichen weathering where Bob Berner didn't believe in the lichen weathering that had been described by Togwell Jackson and his colleagues in Hawaii, because he reckoned that it was a layer of dust and not a proper weathering rind. But what if the dust was of silicate origin? Then it's still going to be weathered, and it's still going to be a source of nutrients for the organisms. And it depends very much, of course, on the morphology of the organism. So if they increase the surface roughness, then they're going to capture an awful lot of dust, and they're going to build up these soils. Whereas if they're flatter, then the amount of soil that they're going to capture is going to also still depend on their morphology. And they're showing here that if there's a single sort of, what do they call that thing? Anyway, if they have a lot of rhizoids or hyphae coming down, then it could be that they'll end up with a void here. Whereas if they don't, then they could end up with more of a solid soil and more material that's ripe for weathering. And now we come, the same paper actually has the bayou tapestry of cryptogamic covers, in my opinion. It's a fantastic figure. So they're showing also like a cyanobacterial dominated crust is going to be quite thin and flat. So it's not going to actually capture very much dust, but on the other hand, it may protect the substrate from being eroded and from having material entrained and then transported somewhere else. So in the context of the Ordovician, were these things there, and were they protecting the landscape from basically aeolian transport? How much dust was there in the atmosphere in the Ordovician? And then if you come over to slightly taller organisms, you're going to capture even more dust. And then if we can just slide to the right of this figure, we're going to continue to capture the increased height of these organisms. You're going to capture even more dust. And then you're going to build up this soil, which weathering is surely going to be taking place in there. And furthermore, the particle size distribution of the dust that's being captured depends on the morphology of the organisms. But I don't actually have a function for that. So again, surface area is one of the most crucial parameters if you're modeling weathering. And it's the one thing that you really have to get right, because all of the underlying equations that I have, those will still be valid in the Ordovician. But if I don't get the surface area right, I mean, it's linearly dependent on this surface area. I have to get it right. So what do I do today? First of all, I have a lithological map. And then I have also a soil depth and particle size distribution, which I received from the vegetation model, which has produced the forcing factors for my weathering model because they're run in series. And then I apply a scaling based on an erosion function, which is a function of how steep the terrain is. And then there may be an additional conversion factor if a lithology is known to have significant internal porosity, for example, because that will increase the surface area. But with a biocrust organism, I mean, I can still perhaps do that, although, I mean, there are clear issues with having a lithological map of the Ordovician. But I could still have a particle size distribution if the vegetation model that I got it from already had it, but then you have to generate that, don't you? And then I also need to know the mineralogy and the particle size distribution of the trapped aeolian material. And then I'm going to also have to have something I've never needed before, and that's the wind, because the wind is going to be crucial for that. And then you need a geomorphological model to model the sediment entrainment and transport, and the protection of the surfaces by the biocrusts. So, and also there are some tantalizing things that I've seen in the literature that biocrusts themselves may have preferences in terms of the substrates as well, because so how to distribute them, I'm not sure that that's ever been taken into account. So what about the water? The water is the other crucial thing. So in this paper of Berry et al., there was an assumption that perhaps for non-vascular plants, so you have wetting and drying events, and then you'd have a dry surface layer forming underneath. And in fact, biocrust type is linked to potential evapotranspiration. And so if you have a very, very arid environment where you're going to have an awful lot of evaporation, then you're more likely to have a cyanobacterial crust. And then if it's a moister climate, you're more likely to have lichens or mosses. Now, mind you, I keep talking about mosses because they're important constituents of modern day systems, but I'm aware of the fact that there's no fossil evidence for them for the Ordovician. So hydrology under biocrust is actually not quite as simple as that diagram sort of implied that it was. And so Jane Belknap has done an awful lot of work on biocrusts, and in her 2006 review, she was looking at different hydrological and also sedimentological parameters related to biocrusts. And so on this end, we have our cyanobacterial crusts, and here we have our sort of larger fruticose lichens and mosses. And we've already discussed that the dust trapping is going to increase. This runoff here is the runoff, the superficial runoff, and basically you have sheet runoff if it's a cyanobacterial crust, and they sort of meander through the hummocks if it's one of these types of crusts. And we've already discussed that the sediment production is likely to change, although I'm not really sure if we can trust this curve because it's generated in modern systems where there is a clear problem with things like cattle trampling on these biocrusts and then increasing them, ruining them as a protective layer and increasing the source area of the dust. So we didn't have any cattle in the Ordovician, so I'm not sure I can really trust this sort of curve. But the surface porosity and the infiltration rate and the soil moisture retention. I mean, surface porosity, I mean, she has it here as decreasing with time, and maybe that's true, but in the papers that I've been able to see so far, it looks like there's all sorts of different things going on with the surface area, the infiltration rates and the soil moisture retention. And indeed, one of her later papers does say that there's just no overarching conceptual framework which will tell us how different biocrusts affect the hydraulic conductivity of the soil, basically. So here's an example of one paper where somebody actually looked at that. So they had a bare soil, and then they had a lichen biocrust, and then they had some vascular plants growing. And they found, of course, that with the bare soil, you know, there was good infiltration and then massive evaporation during the drying phase. But the lichen biocrust, on the other hand, tended to clog up the pores, and it produced an sort of like less permeable layer, so the water had more difficulty infiltrating, and then it also had more difficulty evaporating afterwards, in spite of the overheating that was occurring because the surface albedo had changed, and so it's basically just not behaving like a bare soil at all. Vascular plants, on the other hand, were shading the surface of the soil, and the hydraulics were just completely different from the biocrusts. So three completely different systems, and they didn't look at any sort of taller biocrusts. So what does that mean for me? How do I calculate the hydrological parameters now? Well, since it's being forced by a vegetation model which already calculates those things, I basically have a transpiration rate. So I know like how much water is being exchanged between the rhizosphere and the bulk soil. And I also have soil moisture, and I have the rate at which soil water is leaving the bottom of the soil. So I can actually calculate a sort of mean flow through, and there are no macropores in the vegetation model and no macropores in the weathering model either, to be consistent. But for a biocrust, I have all sorts of unknowns suddenly. I don't know what's going to happen to the percolation. I don't know what's going to happen to the evaporation. And I don't know what's going to happen to the water retention. And I don't know how much, if it's something like a fruticose lichen or indeed a moss, if we were going to model mosses, then we don't know how much water is sort of being protected in the soils that are being developed and amongst the cushions that are being formed. So the cryptogamic critical zone is actually quite different from the vascular plant critical zone. Now, the vascular plant critical zone is usually measured in units of meters, because you can have many meters high canopies and many meters depth of regolith. But here we're talking about a centimeter scale, aren't we? We're talking about a centimeter scale, but then we don't actually know. This doesn't necessarily capture, if the things are growing on sediments which are quite deep, I don't actually know what's happening to a weathering front there. And biocrusts are critical for soil development and substrate stabilization. We still don't know what's going on with the hydrological effects. It's an area of active research amongst the dryland community. But I think if I wanted to do like detailed process-based modeling of the Ordovician, the bottom line is that it comes down to understanding what's happening to the dust and water, and I'm going to leave it there. Thank you.